things that you should be thinking about is that when we exercise, you can think of this as a self-induced fight or flight state. Part of the reason this is true is that anytime you are stressed, so whether it's in fight or flight, in exercise, taking an exam, anything like that, what defines stress is the need for more ATP. And what happens in exercise is that we activate the sympathetic system to prepare our body for exercise, okay? Again, one of the most important things is this increased production of ATP. And so we have our metabolic equation. Where's my pointer here? Oops. So anyway, food plus water equals ATP plus heat plus CO2 food plus oxygen, and you get ATP, heat, CO2, and water. Now, one of the interesting things about exercise is we can actually divide it into two phases. The immediate short-term phase, which is about a minute to a minute and a half, and then the long-term or after the first few minutes. And the reason that we can do this is that we can start thinking about how are you going to immediately start making ATP. Because even if you start with a slow jog or walking, your skeletal muscle needs more ATP instantly, okay? And so in that immediate first part of exercise, you do use what is usually within the muscles themselves. So they are making ATP, but they also have a protein called creatine. And that creatine in rest becomes phosphorylated to become phosphocreatine. They do have their own store of glycogen. Depending on the fiber type, that could be more or less glycogen. And then we also have myoglobin that will actually release oxygen in that first short term of exercise. Those first few minutes are going to buy the time to start delivering more things to the muscles. So you will start increasing glucose as well as fatty acids. They will be broken down, released into the blood. You're going to have more movement of oxygen from the plasma into the tissues. And eventually you are going to have to remove that extra heat and water and some of the metabolites like lactate and CO2. Now, during all of this increased demand, one of the things that is very important is that you are going to have to maintain the energy demands of the brain and the nervous system as well as the vital organs, okay? So what I want to do now is kind of talk about the immediate molecules and mechanisms first and kind of merge it with the long term. So when we think about creatine, creatine is a protein that is in skeletal muscle and cardiac muscle. We do have two different forms, so we can distinguish between the two forms. And most of the time at rest, most of that creatine is converted to phosphocreatine, okay? It is converted to phosphocreatine by an enzyme that is called creatine phosphokinase. An easy way to remember that is California Pizza Kitchen, CPK, okay? So when we're at rest, we're going to take ATP, and with creatine and creatine phosphokinase, we make phosphocreatine and ADP. This is a completely reversible reaction. Just like CO2 and water going to carbonic acid, whichever you have more, whether it's in this case ATP or ADP will drive the reaction in that direction. And so CPK can drive it in either direction. Now, when you're at rest, you're going to have more ATP production, so you convert most of your creatine into phosphocreatine. In fact, this is where we tend to have about 3 times the amount of ATP in skeletal muscle at rest. What I was talking about a few moments ago, I forgot I had this on the slide, when these reactions are completely reversible in chemistry, they're driven by what we call the law of mass action, which means whichever product or substrate you have more of drives the reaction in that direction. Now, this is going to be an easy source to make ATP. And the reason for that is it's one enzymatic step to take ADP and convert it back to ATP using phosphocreatine. So this is going to be one of the ways that we can make a lot of ATP when we first start exercising. Now, one of the other things is that we do need to have oxygen. And skeletal muscle and cardiac muscle has myoglobin. Myoglobin will hold and store oxygen for muscle types, and then at very low partial pressures, we'll be able to release oxygen into the cell itself from its own stored sources, okay? Now, one of the things I also wanted to say, and the next 2 slides, there's not really something per se that you need to know as a hard, cold fact. It is the trends that we tend to see. And what I'm talking about is the trends of what kind of molecules we tend to use as energy sources. So this is one slide, and this is showing you that at rest, muscles tend to use primarily fatty acids as their primary energy source. As you move on to moderate exercise, you will start using glucose, fatty acids, and then some lactic acid. And as you move into heavy exercise, then you start seeing that you're going to use more lactic acid. Now, the reason we tend to use more lactic acid in heavy exercise is lactic acid can be released back into the bloodstream, and it goes to the liver, where the liver will use its ATP to recreate glucose and send it back to the muscle. That may seem like kind of a weird way of doing things, but if a muscle is being activated and it's trying to use all its ATP for cross-bridging or whatever the activities, sodium, potassium, ATPase pumps, et cetera, it doesn't want to use ATP to make more glucose and then break it down. The liver, during exercise, has not really increased its activity. So it can use more ATP to recreate glucose from lactic acid as well as pyruvic acid. Now, another type of profile that we see when it comes to using energy with muscles is shown here. This is actually increasing the duration of exercise. And one of the first molecules we see that tends to be used is muscle glycogen. As we start using up muscle glycogen, we can then start relying on the body to deliver more substances like glucose from glycogen breakdown in the liver and fatty acids from basically breakdown of adipose tissue. Okay? One of the things that I do want to emphasize from both of these slides is that muscles prefer fatty acids as an energy source. There's a reason for this. Number one, from one fatty acid, you tend to get more bang for your buck. You're going to get more ATP produced from one molecule of glucose. The second reason for this is that we don't want to set up a competition between skeletal muscle and the nervous system. If we start taking away glucose from the nervous system, even though action potentials can be produced, the one thing that cannot be produced is more neurotransmitter. So neurons do need ATP for neurotransmitter production and other housekeeping functions. But we don't want to take away from glucose sources. If I go back one slide, you'll see that with respect to glucose, we do have a little bit of surge in moderate exercise, and then it comes back to more of a baseline level in heavy exercise. And then again, in this one, we're going to use muscle glycogen, but actually that muscle glycogen, and then we have an increase in blood glucose, but blood glucose levels are actually maintained because we cannot have a competition between the two tissue types. Now, with respect to making ATP in skeletal muscle, I think you guys are all aware of the fact that there are two main mechanisms or pathways. We have glycolysis, and I'm not going to ask you for the mechanisms, that's a biochemistry class. But in glycolysis, it's important to know that only glucose is used in glycolysis. It occurs in the cytosol. It does not use oxygen. And glucose is broken down to pyruvic acid or pyruvate, which can be converted to lactate acid or lactate. Overall, in this process, there is a net gain of 2 ATP, okay, using one glucose molecule. Glycolysis is believed to be the oldest function. It is used in every single cellular organism on this planet, and we believe that glycolysis has been around at least 3 billion years. So it is one of the oldest ways of making ATP. In our bodies, we also use what is collectively known as the oxidative phosphorylation pathway. This is what occurs in the mitochondria. And in the mitochondria, you can take the breakdown product of glycolysis, so either pyruvic acid or lactic acid or pyruvate or lactate, and it will go into the Krebs cycle. You can also use amino acids, ketone bodies, fatty acids in this cycle, and it is going to be able to produce lots of ATP, but it does require oxygen. Okay, so we have to have oxygen. This is why we have this symbiotic relationship between mitochondria and our cells. So they are going to make massive amounts of ATP for us. Okay? Now, one of the interesting that happens in exercise is that, what happens is that as you start using glucose in exercise, the normal pathway is to produce pyruvic acid, and then you can go into the mitochondria and make massive amounts of ATP. What this slide is trying to show you is not that you ever get into a condition where there is no oxygen, but if you don't have enough oxygen to convert all the lactic acid in the mitochondria, that is considered a no oxygen state for some of those molecules. So you will always be using mitochondria to make ATP, but if you are starting into moderate or heavy exercise, there will not be enough oxygen to convert all of it in the mitochondria, and that's when you tap into that top pathway. So then in that case, this is where you will start seeing lactic acid, and this is where the lactic acid will go into the bloodstream. Now, ironically, when we start seeing lactic acid in the bloodstream, this is how we physiologically define somebody as being in heavy exercise, because that means that the exercise is heavy enough that they're not going to be able to convert all of the pyruvic acid in the mitochondria. One of the other things that I do also want to stress to you guys, these are the different ways in which molecules can be delivered to the skeletal muscle. We can break down fatty acids, and fatty acids can be used by muscle, although then the muscle has to break down the fatty acids with ATP. What is more preferable is that the fatty acids, by and large, are going to go to the liver, and the liver will break them down to ketone bodies. And ketone bodies will then be going to the skeletal muscle. Ketone bodies are 3 carbon compounds, and they can be used immediately in the mitochondria and the oxidative phosphorylation pathway. Glucose we will get from the liver, and then what's missing is it's supposed to say gluconeogenesis on, where's my pointer? Nothing's working. Right here, it's supposed to say gluconeogenesis. I don't know why it's cut off. This is going to be from the pyruvic acid or lactate that goes back to the liver where it can recreate glucose. One of the things that is important to also understand is that the brain uses almost exclusively glucose. And this is why I said earlier we don't want to set up a competition. The brain cells cannot use fatty acids, and they can only use ketone bodies after about 2 weeks of severe starvation. If you are really starving and you have depleted most of your energy sources, that is when neurons will start creating the enzymes that will allow them to actually ferment the lactic acid from the ketone bodies, okay? But ketone bodies normally are not used by the brain. The brain is really using glucose, okay? Now, with those things being said, one of the things to also realize, of course, is that after that first minute of exercise, we're going to rev up the cardiorespiratory system. And so this is going to help to transport more nutrients and waste from and to and away from the skeletal muscle. It will help to maintain blood pressure, transport more oxygen, get rid of CO2, and help to thermoregulate. One of the things that we have talked about in the cardiovascular lab is that the increase in blood flow can go from 5 liters per minute to anywhere from 20 to 30 liters per minute. And so this is also going to result in a change in organ perfusion rates. The perfusion rate is the actual amount of blood going to a particular organ. Muscle perfusion rates easily increase about 10-fold, okay? Whereas other systems will shut down a little bit. This next slide that I have is just to remind you guys, this is a different version of the slide that we showed in the labs where we multiply heart rate times stroke volume to get cardiac output. And again, when you're lying down, you're going to have a slow heart rate. Stroke volume will be up a little bit, but you'll have a little bit over 5 liters per minute. And going on up to running, you're going to have a higher heart rate, higher stroke volume, and a large cardiac output, okay? Now, with respect to this, the other thing to realize, and I'll have you focus on the left image on the slide, when you're at rest, what tends to happen is that as you are pumping blood out of the heart, you're going to get about 13% of the blood going to the brain, 19% to kidneys, 24% to the GI, all the way down to skeletal muscle that gets about 21% of your blood. When you exercise, the percentages of blood going to these organs will differ. And that's what's shown on the right side of this slide. The brain will receive about 3% of the blood. The heart and the skeletal muscle will both receive, the skeletal muscle receives about 88%. The heart will receive 4% as in rest. And these change, okay? Now, the changes in these perfusion rates are due to the sympathetic system. Because throughout the vasculature in our body, I don't know if you guys have heard alpha and beta receptors. So alpha receptors tend to vasoconstrict, and beta receptors tend to vasodilate. And because of the sympathetic system and changing the radius of vessels, we can have more or less percentage of blood flow going to different areas in the body. Now, in looking at this, one of the things that I said on the first slide is that we need to maintain adequate blood flow to the brain all the time. And people started looking at this and they said, wait a minute, at rest, we're sending about 13% of the blood to the brain, but when we exercise, we're only sending 3%. How can that work? Well, what we have to take into account is that cardiac output. And this is also controlled by the sympathetic system. So in cardiac output at rest, we have about 5 liters per minute. If you are sending 13% to the brain, you're going to have about 0.75 liters per minute. When we go down to skeletal muscle, about 1.22 liters per minute. When you are exercising, let's say that your cardiac output has gone up to 25 liters per minute. Well, because that is increased, if you only send 3% of that to the brain, it is still 0.75 liters per minute. So we're able to adjust not only where blood is going, but the amount because of the sympathetic system. We will be able to constrict or dilate vessels, and because of that increased cardiac output, then the vessels that are dilated or even constricted may or may not have more or less blood flow. Even when we have decreased the GI tract to 1%, you are still getting more than adequate blood flow to keep all the cells happy and alive and healthy. But we are going to be able to direct blood where it's needed most, which we're maintaining blood flow to the brain, you're increasing blood flow to the heart, and increasing blood flow to the skeletal muscle. Now, we also have another interesting thing that occurs, and this seems to be something that's intrinsic in individuals. This is something that's called a feed-forward mechanism. And what happens is that when people exercise a lot, when they hear, oh, I'm going to run, or they even think I'm going to run, they start changing their body. And they can increase blood pressure, they can increase heart rate to make sure that there's never a drop. If you think about it, if you maintained your normal cardiac output and your normal heart rate, and you all of a sudden started jogging, you would have a big drop in blood flow. And to kind of illustrate this, when we think, one of the things that is important is this mean arterial pressure. That mean arterial pressure is the driving pressure of blood through the body. It is based on diastolic pressures and systolic pressures. And to remind you guys that the way you calculate it is if you have your blood pressure, let's say it's 120 over 80 millimeters of mercury, your pulse pressure is 120 over minus 80, which is 40. The mean arterial pressure is going to be the diastolic pressure plus 1/3 of the pulse pressure, or systolic minus diastolic pressure, which is normally about 93.33 millimeters of mercury of pressure. When somebody exercises, one of the things that happens, because we start dilating blood vessels to skeletal muscle, your diastolic pressure will be that lower red line because you have dilated the vessels. More blood is staying in the body. If you did not increase heart rate or blood pressure, then your mean arterial pressure would drop maybe even below your diastolic pressure. So what happens when you drop your diastolic pressure, your systolic pressure rises, and that's the blood pressure we're talking about increasing, so that your average stays either at the mean arterial pressure or is actually increased somewhat. Because if you increase it, that will also aid in cardiac output. So, and what I was talking about with the feed-forward mechanism is it seems to be something that is intrinsic. Some people will have a very pronounced feed-forward mechanism. Other people will just have a very moderate. To my knowledge, and I haven't looked in about 10 years, but I have seen nothing that suggests that you can enhance a feed-forward mechanism by exercising. Some people just seem to do it naturally, some do not. If you think about when we did the ECG lab, if your resting heart rate was higher than normal, that is probably representative of a feed-forward mechanism. Where if you exercise, especially when you exercise a lot, if you hear exercise, your brain goes, oh, I'm going out for a five-mile run. And your body just prepares for that, whether it's true or not. Okay, so the next thing we need to talk about is the oxygen. Okay? And oxygen consumption is going to increase from 250 mils per minute to anywhere around 1,500 mils per minute. Your heart rate also goes up, again, easily from 72 beats per minute to 180 beats per minute during exercise. When we think about oxygen, there was a very famous experiment done, and this is actually showing you this experiment, where they knew that the partial pressure of oxygen in the lungs is about 100 millimeters of mercury of pressure. So they bubbled oxygen into a container with just plasma, and then also at the same time with whole blood. So it has the plasma, the red blood cells, white blood cells, everything. And they waited till it equilibrated, and then they analyzed 100 mils of each of the solution. And what they found was that in the plasma, there was about 0.3 mils of oxygen per 100 mils, but in red blood cells, they found 20 mils of oxygen per 100 mils. That's essentially a 70-fold increase. And because of this, this is where they started thinking and viewing red blood cells as oxygen stores. Okay? Now, as they explored how how red blood cells stored oxygen, they realized that it was based on the concentration of oxygen. And partial pressures of gases are kind of representative of gas concentrations. And what they show is that at about a partial pressure of oxygen of about 20 millimeters of mercury, every hemoglobin molecule in a red blood cell will bind one oxygen. Then you have to increase to about 30 millimeters of mercury of pressure, which is increasing the concentration, to get the second molecule to bind. Then you're going to go up to about 40 to get the third molecule bound. But then you have to go all the way up to about 100 millimeters of mercury to get all 4 heme groups per hemoglobin bound with oxygen. And what they realized was there was a cooperation. When one oxygen binds, just like any other molecule, it changes the shape of the hemoglobin, making the second one a little bit easier to bind, the third one a little bit easier, but then there's not really that much of a change, and it's harder to bind that last one, okay? So there is this sigmoid binding of oxygen. It's only at the 100 millimeters of mercury of pressure where every hemoglobin molecule is saturated with oxygen. Now, I'll remind you, there's about 280 million hemoglobin per red blood cell, okay? Now, we also need to kind of review this idea of the changes in partial pressure of oxygen. We can also consider in here the CO2 as we go through the system. In the alveoli, we have a partial pressure of oxygen of about 100 and a partial pressure of CO2 of 40. That will quickly equilibrate with the arterial plasma. And so we are sending through the plasma that partial pressure of gas to the capillaries. That is where oxygen starts moving in. We produce ATP, create CO2, and it moves out. So the key here is that you are varying between, for oxygen, you are varying between 100 millimeters of mercury of oxygen in the lungs and 40 millimeters of mercury or less if you are exercising in the tissues. Now, if I go back one slide here, what that means is that on average, you are only giving up about 1 molecule of oxygen per hemoglobin group every time your blood passes through the body. Even when you are exercising heavily, the partial pressure of oxygen in the blood probably does not drop much below 30. And that means that there are theoretically oxygen molecules that when they bind to a hemoglobin, never unbind. And you do replace hemoglobin all the time, but you're always going to have that reserve. If you have 1 billion oxygen molecules per red blood cell, a quarter of them will never, a quarter to a half, will never be used in your lifetime. Okay? So anyway, this begged the question of early physiologists, well, how do we start getting more oxygen to our cells? Because if we have this change in partial pressure, you would really have to drop the partial pressure in the plasma to increase the oxygen concentration. It wasn't until a Danish physiologist, Christian Bohr, was interested in this, and he did the following experiment. He took plasma, and he slightly changed the pH of the plasma, okay? Now, this binding curve for oxygen, number one, I will tell you that physiologically, we typically refer to it as the oxyhemoglobin dissociation curve. Oxyhemoglobin means hemoglobin that has oxygen bound to it. Not only does it tell us how oxygen binds, but it tells us how oxygen unbinds or dissociates. And what he found, what Bohr found, was that if you made the plasma more acidic, it shifts this curve to the right. So that means that at the same partial pressure of oxygen of 40 here, I can't go up to 40, here is where at a normal pH you're only releasing 1 oxygen per hemoglobin into the plasma, but now you're releasing essentially 2. What that means is that you have increased the concentration of oxygen in the plasma. And going back to Fick's law, we go back to Fick's law a lot, if you have a higher concentration, diffusion is faster. So by shifting this curve to the right, not only could you change the partial pressure of oxygen in the plasma, but you could unload more if the plasma was acidic. If it's basic, it actually holds on to oxygen. This, when he published this, this became known as the Bohr effect. And so then other scientists wanted to say, well, is there anything else that would change this oxyhemoglobin dissociation curve? And what they ultimately found was that basically every byproduct of exercise shifts the curve to the right. So if you have a higher partial pressure of CO2, well, if you're making ATP, CO2 partial pressure will go up. If you have more acid, which Bohr showed, which is a lower pH, that shifts it to the right. And when you're exercising, you're generating temperature. Well, that will also shift it to the right. We also have something in red blood cells called 2,3-bisphosphoglycerate. They use a different pathway to make ATP because they do not have mitochondria. And if they need to make more of this, it will shift it to the right and release more oxygen into the blood. So it turns out that all of these, quote, byproducts of exercise will basically cause a higher concentration of oxygen in the plasma, which will promote faster diffusion and deliver more oxygen to your skeletal muscle. Now, that will ultimately down at the bottom here, the two things ultimately that limit the transfer is the rate at which pyruvate and other molecules are transferred to the mitochondria via your transporters, and then also the maximum heart rate. So it is going to be somewhat limited by diffusion. Okay? Now, when they also saw this, of course, one of the other things that people notice when you exercise is that you start breathing more heavily. And I think in most of my lab sections last week, I tried to emphasize that when you are exercising, you are not hyperventilating. Okay? You are actually increasing the amount of gas exchange, but it is not hyperventilation. And what was very interesting is that initially it was believed that this ventilation rate was regulated by changes in the partial pressure of oxygen and the partial pressure of CO2 in the blood. However, these do not change, not much. And this is actually what we see. If you look on this graph at the very top there, God, where's my cursor? I can't see it. So arterial PO2 stays pretty consistent. And this is the amount of oxygen consumed, which we can use the amount of oxygen consumed to represent the amount of the difficulty of exercise. Arterial PCO2 stays fairly constant until you get to high exercise. Venous PO2 drops a little bit, and arterial pH stays constant until you start releasing lactic acid at heavy exercise. But what was interesting was ventilation went up immediately. What they had expected was there would be a drop in arterial PO2 or a drop in arterial, or sorry, a rise in arterial PCO2. And so this increase in ventilation, it turns out it is a reflex. And so the reason for this is something that we call the VQ ratio. V stands for ventilation, Q stands for perfusion, or the blood flow through a tissue. And these have to be maintained. And I'm going to let you guys find out why in the labs this week. Okay? The last thing I want to talk about right now is the heat. So as we exercise, we do increase the heat production. The reason for that is that every time you take a molecule and convert it to ATP, the conversion from, say, glucose to ATP, all of the energy in the bonds is not transferred. There is always loss of energy, and that creates the body heat. Well, we do have to account and get rid of that heat. Now, it turns out that in our body, there are 4 mechanisms that allow us to exchange heat. We have evaporation, which is fluid leaving our body from sweat. We have radiation, and that is simply heat goes down its concentration gradient like everything else. So if your body is hot and it's cooler outside, it starts to move away from the body. We also have conduction. And conduction, and I should say convection, are kind of similar. If heat is moving away from your body, and if you use a fan, that moves it farther away. So convection will allow you to keep radiating heat. Conduction speeds up that process by, again, from Fick's law, decreasing the distance. So if you put a cool towel on your head when you're exercising, because that's a short distance, it's going to increase the rate at which heat leaves your body. Okay? Now, with respect to these 4 mechanisms, 3 of these, radiant heat, conduction, and convection, only work if the outside temperature is less than body temperature. So on very hot days, the only way to lose excess of heat is through evaporation. Now, a couple things, and I think I'll read off this slide. So temperature regulation at rest. Temperature is about 37 degrees Celsius. The peripheral areas, arms, legs, are a little bit below this, about 2 degrees below. After moderate exercise, the temperature might reach 2 degrees above core temperature. And increased blood flow to the skin produces heat loss by convection, evaporation, and conduction is kind of negligible unless you're helping with that. Flow rate to the skin can increase from 0.15 liters to more than 7 liters per minute. And increased blood flow is mediated through the sympathetic system, which can cause vasodilation. The last thing, fluid balance during exercise. One of the interesting things is that sweat is just a simple filtrate of plasma. So when you are sweating, you are using your plasma to sweat. And sweating can produce up to 30 mils per minute, which is 1.8 liters per hour. I'll let you think about that. How many liters of plasma do we have total? How many liters of blood do we have? About 5. What is a normal hematocrit? 45%. That's about 2.8 liters of plasma total. But you can sweat 1.8 liters per hour. Think about that a little bit, okay? I will tell you, voluntary drinking of pure water can replace only about 2/3 of the water loss. In fact, a huge excess of pure water will actually cause more dehydration. Why do you think that is? Any ideas? I'll let you find out in the lab then, okay?